Imagine the smallest thing you can think of. Go smaller. Go smaller than that. Keep going. Past the atom, past the nucleus, past the quarks spinning inside it, past everything physics has ever actually measured or touched. Keep going until the numbers stop making sense, until the mathematics begins to collapse under its own weight, until space itself, that fundamental universal container that holds everything that has ever existed, simply ceases to be a meaningful concept. You have arrived at the Planck Scale. And here is the thing that should unsettle you before we go any further. You cannot picture it. Not because you haven't tried hard enough. You cannot picture it because the human mind evolved to navigate a world of predators and fruit trees and the distance between here and the river. Your brain has no machinery for this, and nobody does. The physicists who spend their entire professional lives working at this scale, people with 3 decades of graduate mathematics behind them, people who can solve differential equations the way the rest of us make toast. Even they do not have a genuine intuitive grasp of what the Planck scale actually is. They have equations. They have results. They have frameworks so abstract that the frameworks themselves require other frameworks to interpret them. But genuine felt comprehension? Nobody has that. Not yet. Possibly not ever. That honesty should not discourage you. It should thrill you, because what we are about to discuss is not merely a small number. It is not simply the bottom of a ladder you could, in principle, climb down given enough time and a smaller microscope. The Planck scale is the place where the ladder ends, where the rungs are replaced by something so strange that physicists are not entirely sure the word ladder applies anymore. It is the scale at which quantum mechanics, the theory of the very small and general relativity, the theory of gravity, space and time on the larger scales, are both required simultaneously to describe reality. And the terrible beautiful problem is that they are incompatible. When you apply them both at once, the mathematics produces infinities, nonsense answers, division by zero. The universe's way of telling you that you are asking questions it was not designed to answer with the tools you currently possess. So here is the disorienting truth that we need to sit with before anything else. The Planck scale is not a physical object. It is not a particle. It is not even a place exactly. It is a set of natural units, a length, a time, a mass, a temperature that emerge from the mathematics of physics itself when you combine 3 of the most fundamental constants in nature. And when you calculate those units, what you get is a scale so incomprehensibly small that the entire observable universe, all 93 billion light-years of it, is to a single Planck length what a single Planck length is to roughly nothing. There is no human analogy that survives that comparison intact. The Planck length is approximately 1.616 times 10 to the power of negative 35 meters, which means absolutely nothing to your nervous system. So let's try it differently. If you were to take a single proton, the particle at the core of every hydrogen atom in your body, and scale it up until it was the size of the observable universe, a Planck length would be, within that scaled up proton, roughly the size of an actual proton. That is the ratio. A proton inside a universe-sized proton. And physicists believe that below this length, space as we understand it simply does not exist in any form we could recognize. Below the Planck scale, there may be no smooth continuous space. No here and there separated by a distance. Just a seething probabilistic quantum foam, a concept we will return to, where geometry itself becomes undefined, where the idea of being in a location loses its meaning, and where the question, what is happening right now at this point in space, may have no answer. Not because we lack the instruments, but because the question is not well posed. Reality at this scale does not care about your question. And yet this is where all the deepest answers lie, where gravity and quantum mechanics must somehow reconcile, where the origin of the universe is encoded, where the nature of space and time, the fabric of everything, is ultimately decided. We just can't go there. And the story of how we found the edge and what we've been doing at the fence ever since is one of the strangest and most important stories in the history of human thought. It begins, as so many stories of physical measurement do, with a man who wanted to clean up a mess. Max Planck was not, by temperament or reputation, a revolutionary. When he arrived at the University of Berlin in 1889, he was a careful, meticulous, deeply conservative physicist, the kind of man who believed that the great edifice of classical physics was essentially complete, that the remaining problems were matters of refinement rather than reinvention. He was, in his own words, drawn to physics not by a desire to overturn anything, but by a love of the fundamental and the precise. He once admitted that a professor had warned him as a young student that physics was essentially finished and he should consider another field. He had gone ahead anyway, lucky for all of us. The mess that occupied him in the late 1890s was called the blackbody radiation problem. A blackbody is an idealized object, a theoretical material that absorbs all radiation that hits it and emits radiation purely as a function of its temperature. Physicists had been measuring the spectrum of light emitted by these objects and trying to predict it mathematically, and classical physics was failing in an embarrassing way. The equations that worked beautifully at low frequencies broke down completely at high frequencies, predicting that a heated object should emit infinite energy, a result so obviously wrong that it was nicknamed, with genuine gallows humour, the ultraviolet catastrophe. Planck attacked this problem with characteristic methodical patience. He tried every classical approach. None of them worked. And then, in October of 1900, he found a formula that fit the experimental data perfectly. But it required something that had no justification in classical physics whatsoever. It required the assumption that energy was not continuous, that it could only be emitted and absorbed in discrete chunks. Quanta, little packets of a specific size. The size of each packet was proportional to the frequency of the radiation, and the proportionality constant, the number that made the formula work, was a new fundamental constant of nature. We call it Planck's constant. We write it as h. Its value is approximately 6.626 times 10 to the power of negative 34 joule-seconds. Planck presented this result on December 14, 1900, to the German Physical Society in Berlin. He later described it as an act of desperation. He did not believe at the time that he had discovered anything real about nature. He thought he had found a mathematical trick, a clever hack that produced the right answer without meaning much. He was, in the way that only the truly brilliant can be, catastrophically wrong about the significance of his own work. The quantum, the idea that energy comes in lumps, that there is a smallest possible piece of any physical quantity, was real. And within a decade, Einstein would use it to explain the photoelectric effect. Bohr would use it to explain atomic spectra, and the entire architecture of quantum mechanics would begin to rise from the rubble of classical certainty. But Planck had done something else in that 1900 paper, almost as an aside, that would take most of the 20th century to be properly appreciated. He noticed that his new constant, H, combined with two other already known constants of nature, the speed of light, c, and Newton's gravitational constant, g, produced something extraordinary. If you combine these three constants in the right mathematical way, you get units of length, time, mass, and temperature that are derived from nothing but the laws of physics themselves. They require no human reference point. No arbitrary decision about the size of a king's foot or the weight of a grain of barley. No accident of history. They are what they are because of the deep structure of the universe, and any civilization in any galaxy that discovered physics would arrive at the same values. Planck called these his natural units. He described them with a restrained excitement that feels poignant in retrospect as units that maintain their significance for all time and for all civilizations, including extraterrestrial and non-human ones. He had in this quiet little aside identified something that most of his contemporaries ignored completely. The natural units were too small to be physically relevant to any experiment anyone could imagine. The Planck length, for instance, is more than 20 powers of 10 smaller than a proton, and so they were filed away as a mathematical curiosity. An elegant observation, nothing more. The person who would eventually rescue the Planck units from obscurity and understand what they were actually telling us was not born until 1916, the year after Einstein published General Relativity. John Wheeler was an American physicist of extraordinary breadth, a man who collaborated with Niels Bohr on nuclear fission, who worked on the Manhattan Project. He knew who coined the term black hole, and who spent the last decades of his long life obsessed with the deepest question in physics. What is space-time actually made of? Wheeler was the first physicist to take the Planck scale seriously as a physical threshold rather than just a mathematical coincidence. In the 1950s, he proposed that at scales approaching the Planck length, the smooth fabric of space-time that Einstein's equations describe would break down entirely. Quantum fluctuations, the probabilistic uncertainty that governs all subatomic processes, would become so violent at this scale that space itself would bubble and churn and lose its geometric character altogether. He called this quantum foam, and he drew pictures of it, a smooth surface at large scales dissolving, as you zoomed in, into a roiling, probabilistic froth of topology. Wheeler never proved this. He couldn't. The mathematics didn't exist yet, and the experiments certainly didn't. But he had named the abyss. He had given the physics community a word for the place where physics, as they understood it, stopped working. And once you have named something, you cannot unsee it. So how small is the Planck length really? Not in a way that satisfies the equation, in a way that lands somewhere in the chest. Start with something you know. A human hair. Yours, let's say. It is roughly 70 micrometers in diameter, about 70 millionths of a meter. That seems small. Peer into it under a magnifying glass, and you can see the individual scales of the keratin fiber. Go smaller. The width of a DNA strand, the molecule carrying the instructions for every living thing on this planet, is about 2 nanometers, 2 billionths of a meter. Still comprehensible if you squint hard enough. Now an atom, a hydrogen atom, the simplest, oldest, most abundant atom in the universe, has a diameter of about 1/10 of a nanometer or 1 angstrom, 1/10 billionth of a meter. You need an electron microscope to see anything at this scale. The hair is now 100,000 times larger than the atom, but the atom is not the bottom. Inside the atom is the nucleus, which is roughly 100,000 times smaller than the atom itself. If you inflated a hydrogen atom to the size of the Colosseum in Rome, that grand circle of ancient stone, 188 meters across, the nucleus inside it would be the size of a grain of sand at the center. A proton, one of the particles in that nucleus, sits at roughly 1 femtometer in size, 1 quadrillionth of a meter, 10 to the power of -15. Physicists probe this scale with particle accelerators, machines that smash particles together at energies approaching the speeds of light, reading the wreckage to understand the structure of matter. The Large Hadron Collider at CERN, which took 20 years and $10 billion to build, probes scales of roughly 1/1000th of a proton's width. That is as deep as humanity has physically looked into the structure of matter. And if you want a sense of what that represents geographically, the LHC's main ring is 27 kilometers in circumference, buried roughly 100 meters beneath the Swiss-French border. It is an object you could see from the air, an enormous thing built to look at something unimaginably small. That ratio already strains the imagination. Now take that proton width, that femtometer, that 10 to the power of -15 meters, and understand that the Planck length, 10 to the power of -35 meters, is 20 orders of magnitude smaller, 20 powers of 10. To cross that gap with the LHC, you would need an accelerator with 1,000 billion times more energy than it currently produces. If you built that accelerator in a straight line with current technology, it would need to be longer than the observable universe. Not very long, longer than everything we can see in any direction. This is not an engineering challenge we will overcome with better funding and a new facility. It is a fundamental statement about the relationship between energy and scale in physics. The smaller you want to probe, the more energy you need, and the energies required to probe the Planck scale are energies that do not fit inside the universe as it currently exists. Here is another way to feel it. A single Planck time, the time it takes light to cross one Planck length, is approximately 5.39 times 10 to the power of -44 seconds. The universe is about 13.8 billion years old. If you represented the entire age of the universe as a single year, one calendar year from the Big Bang to right now, one Planck time within that year would be incomparably smaller than the smallest interval any clock has ever measured, by a margin so vast that the comparison collapses. The Planck time is to 1 second, as 1 second is to roughly 300 trillion times the current age of the universe. Put it another way, in the time it takes a single photon of light to travel across a single proton, approximately 10 to the power of 20 Planck times have elapsed. That is 100 billion Planck time intervals just in that crossing. Time, at the Planck scale, is granular beyond any number your intuition can metabolize. There is also the Planck mass, which is peculiar in its own right, approximately 21.76 micrograms, roughly the mass of a single grain of fine sand. But this is the mass of an object compressed to a Planck-length volume. At that density, quantum gravity effects become dominant, and no semi-classical description of space survives. Density, like length and time, has a threshold at the Planck scale, and that threshold sits approximately 59 orders of magnitude above the density of water. The difference in those two numbers represents the entire gap between a glass of water and the edge of physical description. If the atom is like Mount Everest relative to a proton, the proton is like Mount Everest relative to the Planck length. And even that metaphor fails, because Mount Everest is only about 1 billion times taller than a proton. You need another 20,000 Everests, stacked on Everests, before the ratio becomes accurate. The universe does not give you the geography to stand at this scale and look around. It gives you only the mathematics, and the mathematics says, here is the edge of the map. And yet the map shows something on the other side, faint, terrifying, unbeautiful. Hints of what space is at the bottom, if it is anything at all. To understand why the Planck scale matters, why it is not just the world's smallest irrelevant measurement, you need to understand the problem it sits at the center of. And that problem is the deepest unsolved problem in theoretical physics, perhaps in all of science. Physics currently rests on two incompatible pillars, They are each spectacularly successful on their own terms. Together, they are logically inconsistent. The contradiction between them is the central intellectual crisis of our age, and it lives in its most concentrated form right at the Planck scale. The first pillar is general relativity. Einstein published it in 1915, and it remains one of the greatest intellectual achievements of any individual in history. A statement about the nature of gravity, space, and time so radical that even a century later, its core ideas resist easy assimilation. The short version, and every short version is a slight injustice, is that gravity is not a force. It is a curvature. Mass and energy warp the fabric of space-time, and what we experience as the pull of gravity is simply the motion of objects following the straightest possible paths through a curved geometry. The Earth orbits the Sun not because some invisible force is pulling it inward, but because the Sun's mass bends space-time into a shape where the Earth's path curves around it. This is not metaphor, it is geometry, and it is, as far as we can measure, exact. Think of a heavy bowling ball placed on a stretched rubber sheet. It makes a depression. A marble rolled nearby curves toward the depression not because the ball is attracting it, but because the sheet itself is curved and the marble follows the curved surface. This is Einstein's picture of gravity. The rubber sheet is space-time, the bowling ball is a massive object like the Sun, and every planet, photon, and comet follows the curved geometry that mass creates. The rubber sheet analogy breaks down in the details. Real space-time curves in 4 dimensions, not 2, and it curves in time as well as space. But it captures the core insight. Gravity is geometry. General relativity treats space-time as smooth, continuous, and deterministic. Given the state of a physical system now, the equations of general relativity will tell you precisely, unarguably, what that system will look like at any future time if you have enough information about the matter and energy inside it. Space-time in general relativity is a 4-dimensional manifold, a surface, not made of anything, just the stage on which physics happens. The equations that describe this, Einstein's field equations, are actually 10-coupled, non-linear, partial differential equations, and solving them exactly is so difficult that it had to wait years after publication for Schwarzschild and others to find specific solutions. But the framework is complete. It admits no ambiguity, no probability, no fuzziness. Given the starting state, the future is determined. The second pillar is quantum mechanics, refined over the course of the 20th century into quantum field theory, the framework that describes every particle, every force except gravity, and every interaction between them. Quantum mechanics is, by any measure, the most precisely tested theory in the history of science. Its predictions match experiment to better than 1 part in a trillion. It has never, not once, made a prediction that was measurably wrong. And its central claim about reality is that the universe, at its most fundamental level, is not deterministic. It is probabilistic. Before you measure a quantum system, it does not have a definite state. It exists in a superposition of possible states. When you measure, the wave function collapses, and you get one of those possibilities, with a probability determined by the mathematics. But before measurement, there is no fact of the matter about what the system is doing. A favourite illustration involves Schrödinger's cat, the thought experiment in which a cat inside a sealed box is simultaneously alive and dead until you open the box and look. Schrödinger intended this as a reductio ad absurdum, a way of pointing out the apparent absurdity of applying quantum superposition to macroscopic objects. But the joke is on classical intuition. The underlying phenomenon is real. Electrons genuinely exist in superpositions of spin states until measured. Photons genuinely travel through both slits simultaneously in the double-slit experiment. The universe at its core is, strangely, irreducibly probabilistic, not because we lack information as Einstein believed. God does not play dice, but because the universe genuinely does not commit to a single outcome until an observation is made. Bell's theorem, confirmed experimentally by Alan Aspect in 1982, and for which Aspect, Klose, and Zeilinger received the Nobel Prize in 2022, proved definitively that no theory of hidden local variables can reproduce quantum mechanical predictions. The probabilities are real. The indeterminacy is fundamental. Quantum mechanics also has something else built into it that makes it fundamentally incompatible with general relativity, the uncertainty principle. Formulated by Werner Heisenberg in 1927, it states that there are pairs of physical properties, position and momentum, energy and time, that cannot both be precisely defined at the same moment. This is not a limitation of measurement instruments. It is a fact about reality. The universe does not have, at the quantum level, precise simultaneous values for both members of these conjugate pairs. The more precisely you know one, the less precisely the other is defined, not because you disturb the system by measuring it, but because the system genuinely does not have both values at once. Now watch what happens when you try to bring these two pillars together. General relativity requires space-time to be smooth and continuous. Quantum mechanics says that any system pushed to small enough scales and high enough energies will fluctuate wildly and probabilistically. The energy of empty space in quantum field theory is not zero. It is a seething sum of virtual particle pairs constantly popping in and out of existence, a phenomenon confirmed by the Casimir effect and the Lamb shift and dozens of other experiments. If you apply this quantum fuzziness to space-time itself, you are applying quantum mechanics to gravity. And when you try to do that calculation, when you try to compute what gravity looks like at very small scales using the standard tools of quantum field theory, the answers come back as infinities. Not large numbers. Infinities. Mathematical nonsense. Every calculation produces a result of infinite energy, infinite curvature, infinite everything. What is going wrong precisely? Consider what the uncertainty principle implies for very small volumes. To know precisely where you are in space, you need to confine yourself to a small region. To confine a quantum particle to a very small region, a volume of Planck size, say, the uncertainty principle dictates that the momentum of the particle in that region is enormously uncertain. Momentum means energy. Enormous uncertainty in momentum means enormous uncertainty in energy, which means that the energy concentrated in that tiny volume is, on average, enormous. Energy curves space-time according to general relativity. Enough energy in a small enough volume collapses into a black hole. So when you try to squeeze quantum mechanics and general relativity together at the Planck scale, you discover that the very act of probing that scale, of trying to say something is here, creates a black hole of Planck mass. The probe collapses into the thing it was trying to measure. The two theories eat each other. This is not a metaphor for an incompatibility. It is the incompatibility expressed geometrically. Physicists call this the problem of quantum gravity, and the scale at which this problem becomes unavoidable, the scale at which quantum effects in gravity can no longer be ignored or perturbatively suppressed, is the Planck scale. Below the Planck length, you cannot pretend that space-time is classical and smooth. The quantum fluctuations of geometry are of the same order of magnitude as the geometry itself. The stage starts acting like a player. Space-time stops being a backdrop and becomes a dynamical quantum object, and our mathematics has for over a century simply not been adequate to describe it. This is not a gap in the theory, it is a fundamental breakdown. The two most successful theories in the history of physics, theories that together account for effectively every physical phenomenon we have ever observed, are incompatible, and the incompatibility becomes absolute at the Planck scale. Something has to give. Either general relativity is wrong at very small scales, or quantum mechanics is wrong at very high energies, or both are approximate descriptions of some deeper theory that reduces to each of them in the appropriate limit. And finding that deeper theory, a theory of quantum gravity, is the central quest of theoretical physics, has been for 100 years. Before examining the candidates for that theory, it is worth pausing on why the three natural constants that produce the Planck units, h, c, and g, are so significant individually, and what it means that combining them produces a length. Planck's constant h governs the quantum world. It sets the scale of quantum uncertainty, the size of quantum jumps, is the minimum lump of action in any physical process. The speed of light c governs relativistic physics. It is the universal speed limit, the constant that relates energy to mass in Einstein's E equals mc squared, and the constant that makes special relativity internally consistent. Newton's gravitational constant g governs the strength of gravity. It determines how much space-time curvature a given mass produces, how strongly planets attract each other, how quickly stars form from collapsing gas clouds. Each of these constants defines a completely different domain of physics: the quantum, the relativistic, the gravitational. When you combine all three into a single unit of length, you are building the only length scale in nature that requires all three domains simultaneously. That is precisely the Planck length significance. It is the scale where quantum mechanics, relativity, and gravity all become comparably important at once. It is the scale where you can no longer do quantum physics while ignoring gravity, or gravitational physics while ignoring quantum effects. The Planck units are the fingerprint of the place where everything meets. There are candidates for the theory that describes what happens at that meeting. Three main ones, each with its own community of brilliant advocates, its own decades of development, its own partial successes and frustrating failures. The most mathematically developed is string theory. The central idea is simple enough to state, though the mathematics involved is anything but. The fundamental objects of nature are not point particles, but one-dimensional strings of energy. A string vibrating in one mode is an electron. Vibrating in another mode, it is a photon. Vibrating in yet another, it produces a graviton, the hypothetical quantum carrier of gravity. The appeal of string theory is that gravity emerges naturally from the mathematics of strings in a way that avoids the infinities that plague conventional quantum field theory. The strings have a minimum length related to the string tension, and this minimum length in the standard formulation of string theory is comparable to the Planck length. String theory therefore naturally incorporates the Planck scale as a physical threshold. The problem with string theory, which its critics have not tired of pointing out since the 1980s, is that it has not produced a single experimentally confirmed prediction. It requires extra spatial dimensions, typically 6 or 7 of them, curled up at the Planck scale and invisible to current experiments. It seems to admit an almost incomprehensibly vast number of possible versions. The landscape of string theory contains something like 10 to the 500 possible vacua, each describing a different universe with different physical constants, and selecting which one corresponds to our universe has proven intractable. String theory is either the deepest idea in physics or the longest running detour from it, and honest practitioners will tell you they genuinely do not know which. The main competitor is loop quantum gravity, developed principally by Lee Smolin and Carlo Rovelli, beginning in the 1980s. Where string theory starts from the standard model of particle physics and tries to include gravity, loop quantum gravity starts from general relativity and tries to quantize it directly. Its central result is that space itself is quantized, that at the Planck scale, geometry is not continuous but discrete. Space comes in minimum chunks, spin networks of Planck scale size. You cannot subdivide a Planck length. There is no smaller piece. Space is granular at its foundation, the way matter is granular at the atomic level. Time, in loop quantum gravity, also emerges as quantized, proceeding in discrete Planck time steps rather than as a continuous flow. Loop quantum gravity has the virtue of mathematical background independence. It does not assume a fixed space-time backdrop, but derives geometry from the quantum state of the theory itself. It has produced some concrete results, including a resolution of the classical singularity at the center of a black hole and at the Big Bang, replacing them with bounces to new regions of space-time. But it also has not yet produced experimentally testable predictions that distinguish it from its competitors, and connecting it back to the smooth space-time of general relativity at larger scales has been technically difficult. There is a third approach, less famous but gaining attention: causal dynamical triangulations and related programs called asymptotic safety. These approaches attempt to define quantum gravity through path integrals over different possible geometries, looking for a self-consistent theory that avoids the infinities without requiring strings or the discrete space of loop quantum gravity. They are computationally intensive, often pursued through numerical simulation, and have produced some tantalizing results, including the emergence of a four-dimensional spacetime from lower-dimensional quantum geometries at very high energy. The asymptotic safety program, pioneered by Steven Weinberg and developed in careful detail by Martin Reuter and Frank Saueressig, proposes that gravity may be non-perturbatively renormalizable after all, that the coupling constants of gravity run to a finite ultraviolet fixed point as you increase energy toward the Planck scale instead of diverging. If true, this would mean you do not need new fundamental objects like strings or a discrete space-time to cure the infinities. You need the right mathematical treatment of geometry itself. All of these frameworks, despite their differences, agree on one thing: the Planck scale is where the answer lives. Whatever quantum gravity turns out to be, its effects will be concentrated at, or expressed most purely at, the Planck scale. It is the locked room at the heart of physics. Everyone agrees it contains the most important secret in nature. Nobody yet has the key. Here is where honest science has to be uncomfortable. Because the problem with studying the Planck scale is not merely that it is difficult, it is that it may be, in any direct experimental sense, permanently beyond reach. And that is a genuinely unusual situation for physics to find itself in. Physics has always been, at its core, an empirical science. You propose a theory, you derive predictions, you test those predictions with experiments. If the experiments confirm the predictions, the theory survives. If not, the theory dies or is revised. This cycle, hypothesis, prediction, experiment, is the engine of scientific progress. It has driven everything from Galileo dropping objects off the Leaning Tower of Pisa to the detection of gravitational waves by LIGO in 2015. The cycle works. At the Planck scale, the cycle jams. The gap in energy between current experimental capability and Planck energy is, as noted earlier, approximately 20 orders of magnitude. The LHC, which is already the most complex machine ever built by human beings, probes roughly 10 to the power of 4 giga-electron volts. Planck energy is approximately 10 to the power of 19 giga-electron volts. To probe the Planck scale directly with a particle accelerator, you would need to increase our experimental energy by a factor of 1 quadrillion. This is not a technology problem in the ordinary sense, it is a physics problem. The energy required to create a Planck scale probe in a small region of space would, by the equations of general relativity, collapse that region into a black hole. The probe would eat itself before it could return a result. This has led to a genuine and uncomfortable debate within the physics community about what it even means for a theory of quantum gravity to be scientific if it cannot be tested. String theory has been particularly criticized on these grounds. The philosopher Richard Dawid coined the phrase non-empirical theory assessment to describe the process by which string theorists evaluate their work. And the physicist Lee Smolin argued in his 2006 book that string theory's untestability represented a crisis for the field. The debate is not merely about string theory, it is about the entire enterprise of Planck scale physics. How do you do science at a scale you can never directly observe? The answer, to the extent there is one, involves looking for indirect signals. The universe itself, in its earliest moments, was a Planck scale environment. In the first Planck time after the Big Bang, that almost nothing unit of time we calculated earlier, the entire universe was compressed into a region of Planck density. And quantum gravitational effects were not merely important, but dominant. The patterns left in the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills the entire sky, might, in principle, encode information about quantum gravitational physics from that earliest epoch. Detecting that signal would require extraordinary precision, and separating it from the noise of everything that happened in the subsequent 13.8 billion years is a formidable challenge. But it is not obviously impossible. Similarly, some models of quantum gravity predict that the speed of light might be very slightly energy dependent at Planck scales, that very high energy photons and very low energy photons, produced in the same gamma ray burst billions of light years away, might arrive at Earth at slightly different times if space-time is granular at the Planck scale. The Fermi Gamma Ray Space Telescope has been looking for exactly this signal, and so far the photons arrive together, placing tight limits on the size of any Planck scale dispersion. This does not rule out all models, but it rules out some, and that is real, if indirect, progress. There is also the question of Hawking radiation, the process predicted by Stephen Hawking in 1974, by which black holes slowly evaporate by emitting thermal radiation, a consequence of applying quantum field theory to the curved space-time near a black hole's event horizon. If Hawking radiation is real, and the theoretical case for it is strong, then information about the quantum structure of space-time might be encoded in it. But we have never detected Hawking radiation directly. The black holes for which it is most relevant are primordial micro-black holes, objects the size of the Planck length with masses of the Planck mass, and their existence is theoretical. We have not found one. The honest summary is this: we have a map of where the answer should be, we have several theories about what the answer might look like, and we have so far no direct empirical access to any of them. The Planck scale is the one place in physics where theory has dramatically outrun our ability to test it. And that creates a scientific culture, particularly around string theory, where brilliant people can spend entire careers developing ideas without a single experiment to constrain them. Whether that is physics or philosophy is a debate that has not been resolved. Let's take the journey inward. Let's start from where we are and travel down into the structure of matter, following the history of discovery. until we arrive at the bottom of the ladder and find out what the physicists found when they looked over the edge. The first serious journey inward began with John Dalton in the early 19th century. Dalton, a Quaker schoolteacher from Cumberland with no formal laboratory and a face that seemed permanently surprised by its own thoughts, proposed in 1803 that matter was made of atoms, indivisible, indestructible particles, each element having its own kind. This was not new as a philosophical idea. The ancient Greeks had their atomists, Leucippus and Democritus, who imagined a similar thing 2,000 years earlier. What Dalton added was quantification. He measured atomic weights from chemical reactions and produced the first table of elements by mass. He gave the atom a number, if not yet a face. The face came courtesy of J.J. Thomson, who in 1897 discovered the electron, a particle inside the atom with a negative charge, far lighter than any atom. The atom, it turned out, was not indivisible after all. It had parts. Thomson imagined these electrons embedded in a diffuse sphere of positive charge, like plums in a pudding, a model that turned out to be completely wrong, but which, with characteristic British understatement, served its purpose until something better came along. The something better came from Ernest Rutherford in 1909 in an experiment that Rutherford himself described as the most astonishing result of his life. He and his collaborators, Hans Geiger and Ernest Marsden, fired alpha particles, helium nuclei, at a thin sheet of gold foil, expecting them to pass straight through with minor deflections. Most of them did, but some bounced straight back. It was almost as incredible, Rutherford said, as if you fired 15-inch shells at tissue paper and they came back and hit you. The atom, they discovered, was almost entirely empty space. Its mass was concentrated in a tiny, dense nucleus at its center, with the electrons orbiting around it at vast relative distances. The atom was not solid. It was a solar system in miniature, with a tiny sun at the center and planets at proportional distances so large that the atom was, by volume, practically nothing. Now here is where the journey gets stranger. Rutherford's nuclear model was followed. Over the next decades, by the discovery of the proton and neutron inside the nucleus, and then, in the 1960s and 1970s, by the discovery that protons and neutrons were not fundamental either. They had structure. They were made of quarks, smaller constituents bound together by the strong nuclear force carried by particles called gluons. The theory of this binding, quantum chromodynamics, QCD, was one of the triumphs of the standard model of particle physics, developed through a remarkable collaboration of theorists and experimentalists across 2 decades. By the mid-1970s, the standard model was essentially complete, and it described all known matter and all known forces except gravity in terms of a small number of fundamental particles, 6 quarks, 6 leptons, 4 force-carrying bosons, and, added later, the Higgs boson, and confirmed by the LHC in 2012. The question then was whether the quarks and leptons were themselves fundamental. Could you go smaller? The answer, as far as current experiment can say, is that they appear to be. Quarks and electrons do not seem to have internal structure at any scale we can probe. They behave within the precision of our instruments as point particles, objects with no spatial extent. But here is the problem. A truly mathematical point with exactly 0 size is physically pathological. When you try to calculate the energy of a point electron in classical electromagnetism, you get infinity. The electron's own electric field, infinitely concentrated at a point, has infinite energy. This infinity was one of the central crises of 20th century physics, and quantum field theory resolved it, imperfectly and ingeniously, through the procedure of renormalization, a mathematical technique that isolates and subtracts the infinities, leaving finite, measurable predictions. Richard Feynman, who did as much as anyone to develop renormalization, called it a dippy process and hocus pocus, while freely admitting that it produced the right answers to extraordinary precision. The infinities never went away. They were managed, and management has its limits. Now travel further inward, not in the lab, but in the mathematics. In the 1970s and 1980s, theorists began seriously exploring what the structure of space-time itself might look like at scales approaching the Planck length. John Wheeler's quantum foam, that image of space-time dissolving into probabilistic froth, became a formal object of study. In loop quantum gravity, as Carlo Rovelli worked through the mathematics of quantizing general relativity, what emerged was a description of space not as a smooth continuum, but as a kind of network, spin foam, where the nodes of the network represent quanta of volume and the links represent quanta of area. The fundamental quanta of area in loop quantum gravity is of order the Planck length squared. Below this scale, the concept of area becomes undefined. The geometry is not small, it is absent. Think about what this actually means. You are standing on the floor. The floor has an area. If you paint a circle on the floor, that circle has an area. If you halve the radius of the circle, the area drops by 3/4. You can keep halving. In mathematics, you can do this forever. The circle gets smaller and smaller, approaching zero but never reaching it. The area decreasing continuously all the way down. Smooth, continuous, infinite divisibility. In loop quantum gravity, you cannot actually do this. At some point, the Planck scale, you hit the smallest possible area. You cannot halve the circle anymore. The geometry discretizes. You cannot have half a quantum of area any more than you can have half an electron. The floor, at the bottom, is pixelated, not in a metaphorical sense, in a literal, mathematical, fundamental sense. In string theory, the equivalent statement is different but leads to a similar place. Strings cannot probe distances smaller than the string length, which is near the Planck length, because you would need more and more energy to probe smaller scales, and at some point, adding energy to a string does not make it probe smaller scales, but instead makes it wrap around compactified extra dimensions or creates other effects that prevent the probe from functioning. In string theory, there is a minimum distance built into the physics. T-duality, a remarkable symmetry that equates physics at small distances with physics at large distances, meaning that going smaller below the string scale actually takes you to a physically equivalent large-scale description. The concept of smaller loses its meaning at the string scale. In causal set theory, a less developed but elegant approach, space-time itself is discrete from the ground up. The universe is a partially ordered set of events, and the order relations between events define the causal structure of space-time. The density of events in this framework is one event per Planck volume. Space-time is not a continuous manifold that happens to have a minimum length. It is, at its foundation, a network of discrete points. Lorentz invariance, the symmetry of special relativity, turns out to be preserved on average in causal set theory, even though the discrete structure might seem to violate it at the scale of individual events. All of these frameworks, string theory, loop quantum gravity, causal dynamical triangulations, causal sets, are different maps of the same locked room. They disagree on what is inside, but they all agree on where the room is, at the Planck scale. And as you travel down through the scales and approach the edge, what you find in every theoretical framework is not simply a very small version of the ordinary universe, but something categorically different. And space that is discrete, time that is quantized, geometry that fluctuates, causality that is statistical rather than certain. The journey ends in every framework at the same place, the edge of the describable. The point where the physics we have stops working and the physics we need has not yet been written. And what is particularly striking, what makes the Planck scale so different from every other frontier in science, is that it is not a frontier you can simply approach more closely with better instruments. You approach it mathematically. You travel there in the equations, and the equations stop making sense before you arrive. There is a thing that physicists working on quantum gravity have learned over the decades to live with, and that newcomers to the field find deeply uncomfortable. Yeah, and it is this. The theories they are building have no experimental guidance. None. The Planck scale is not just hard to access, it is, for all practical purposes, inaccessible. And when science operates without experimental feedback, strange things can happen to it. The history of theoretical physics has, to be fair, seen this before. When Einstein was developing general relativity, there were no precision GPS systems to test it, no gravitational wave detectors, no direct images of black holes. He worked from aesthetic criteria, the beauty of the mathematics, the principle that physical laws should look the same to all observers, and produced a theory that turned out to be correct. The aesthetic sensibility was not a substitute for experiment. It was a guide to the structure of the right equation. And when the experiments finally came, the bending of light during the 1919 solar eclipse observed by Arthur Eddington, the precession of Mercury's perihelion, and ultimately the LIGO detection in 2015, the theory passed every one of them. Beauty, in that case, was a reliable guide. String theory was developed with similar aesthetics. It is, by any mathematical standard, extraordinarily beautiful. The idea that all particles are vibrations of a single fundamental type of object, that the diversity of matter and force reduces to the harmonics of a string, has an elegance that many physicists find compelling on its face. But general relativity was beautiful, and also relatively quickly testable. String theory is beautiful, and so far not. And the fear, a fear that responsible physicists acknowledge openly, is that beauty can mislead you. That you can spend decades in a mathematical labyrinth because the architecture is gorgeous, without any way to verify that it corresponds to the actual universe, rather than to one of the 10 to the 500 other universes the theory accommodates. This is the landscape problem, and it is not solved. Lee Smolin, in a 2006 assessment that sparked considerable anger within the string theory community, argued that string theory had monopolized theoretical physics talent for 2 decades without producing a single testable prediction, and that this represented a kind of intellectual monoculture that was actively harmful to the field. He was not entirely wrong, though he was not entirely right either. His string theory had produced genuinely important results. The ADS/CFT correspondence, developed by Juan Maldacena in 1997, which relates certain string theories in curved space-time to quantum field theories on the boundary of that space-time, has been extraordinarily productive as a tool for studying strongly coupled quantum systems. Its applications in condensed matter physics, in understanding the quantum mechanics of black holes, in nuclear physics, these are real. The theory is not merely speculation, but it is not yet physics in the experimental sense. And there is a deeper worry, because the Planck scale is not just experimentally inaccessible at the present. The numbers suggest it may be experimentally inaccessible in principle, for any civilization constrained by the laws of our universe. To build a collider that reaches Planck energies, you would need a machine so large and so energetic that it would itself collapse into a black hole before it operated. This is not a cost problem, it is a logical problem, and it means that theoretical physics, at the Planck scale, may be permanently operating in an empirical vacuum. The question this raises, and it is a genuinely important one, is whether the scientific method requires modification when applied at this frontier. Do we need new criteria for theory evaluation? New notions of what counts as a successful scientific explanation? The philosopher of science Richard Darwin has argued yes, that certain theoretical virtues, like internal mathematical consistency, the unification of previously separate theoretical frameworks, and the absence of alternatives, either can serve as evidence in the absence of experiment. Most physicists are uncomfortable with this. Most philosophers of science are even more uncomfortable with it, but the discomfort does not make the problem go away. What it means practically is that we are in a period of theoretical physics where the most important ideas may be unverifiable, where competing frameworks may all be internally consistent and mutually incompatible, and where the final arbitration by experiment, the thing that makes physics physics, may be indefinitely delayed. The honest position is to say, this is where we are, it is frustrating, and it does not mean that the work is pointless. It means that the frontier of knowledge has temporarily outrun the frontier of measurement, and that this has happened before, and that patience is the only virtue available. Now, here is something that the standard story of the Planck scale almost always leaves out. There is a corner of this discussion that attracts the credulous, the frustrated, and occasionally the genuinely heterodox. And it is worth walking through it, because not everything in the fringe is purely wrong, and dismissing it wholesale misses an opportunity to understand why the mainstream is where it is. The most persistent fringe claim around the Planck scale is that it represents evidence for a simulated universe. The argument in its most coherent form goes like this. If space is quantized, if it has a minimum length, then space looks like pixels. And if space looks like pixels, then space is computation. And if space is computation, then space is running on something, a computer, a higher dimensional computer, built by some incomprehensibly advanced civilization running a simulation of a universe, and we are inside it. The pixelation at the Planck scale is the resolution limit of the simulation. This is not an idea invented by YouTube commenters. Nick Bostrom, a serious philosopher at Oxford, published a formal version of the simulation argument in 2003, arguing that at least one of three propositions must be true. Virtually all civilizations go extinct before developing simulation-capable technology. Virtually all sufficiently advanced civilizations choose not to run detailed simulations of past civilizations. Or we are almost certainly living in a simulation. The argument is logically valid, and some serious physicists, including Elon Musk, who is not a physicist but speaks like one sometimes, have endorsed it. The problem, from a physics standpoint, is that discretization of space in loop quantum gravity or causal set theory does not actually imply computation in any meaningful sense. Physical discreteness is not the same as informational pixelation. A crystal lattice is discrete. Its atoms sit at specific points. But nobody argues that crystals are running a simulation. The analogy between Planck scale discreteness and computational pixels requires several additional assumptions that are not supported by the theories. Loop quantum gravity does not produce a regular grid. The spin network geometry is dynamical and irregular in a way utterly unlike a computational mesh, and the information theoretic arguments that underpin the simulation hypothesis remain deeply contested. More interesting, though less viral, is the holographic principle, a serious theoretical idea arising from the work of Gerard 't Hooft and Leonard Susskind in the 1990s, inspired by Bekenstein and Hawking's discovery that black hole entropy is proportional not to the volume of the black hole, but to its surface area. The holographic principle proposes that the information content of any region of space is determined by the area of the region's boundary, not its volume. And that area, at the Planck scale, is quantized in Planck units. This is the foundation of the ADS/CFT correspondence, which is one of the most productive ideas in theoretical physics of the last 30 years. It is not simulation. It is a deep statement about the relationship between bulk physics and boundary physics, and it may hold the key to resolving the black hole information paradox, which is itself one of the deepest problems at the intersection of quantum mechanics and gravity. There are also serious physicists who have proposed on various grounds that the cosmological constant, the energy of empty space responsible for the accelerating expansion of the universe, might be naturally explained by quantum gravitational effects at the Planck scale. The problem is that the naive quantum field theory prediction for the cosmological constant, based on the energy of quantum vacuum fluctuations up to the Planck energy, is approximately 120 orders of magnitude larger than the observed value. This is the largest discrepancy between theory and observation in the history of physics, and it is sometimes called the worst prediction in physics. Understanding why the cosmological constant has the value it does, why the vacuum energy is almost but not quite zero, is thought to require Planck scale physics. This is not fringe. It is one of the most urgent open problems in fundamental physics. What the fringe and the frontier share is a recognition that the Planck scale is not merely the bottom of the ladder. It is the threshold of something, the question of what. Now step back from all of it. Step back from the strings and the spin networks and the causal sets and the quantum foam. Step back from the uncertainty principle and the landscape problem and the ultraviolet catastrophe and the renormalization procedure. Step back from the equations and look at what is actually happening here. We have built, over the course of 2.5 millennia, a ladder of understanding that reaches from the scale of human experience all the way down to the Planck length. We have, at each rung of that ladder, discovered that what we thought was fundamental was not, that the solid was made of atoms, that the atom was made of nucleus and electron, that the nucleus was made of protons and neutrons, that the protons were made of quarks. At each step, the universe revealed a new layer beneath the one we thought was the bottom. The layers do not obviously stop. But at the Planck scale, physics itself gives out. Not our physics, but physics, the enterprise of describing nature with mathematics. The mathematics does not fail because we haven't been clever enough yet. It fails because we have written 2 sets of equations for the universe and they are incompatible, and the incompatibility becomes fatal exactly here. This is the moment of genuine reframe. What we think of as the Planck scale, as the bottom of physical reality, may actually be something quite different. It may be the bottom of a particular way of asking questions about reality. The failure of quantum field theory and general relativity at the Planck scale may not be telling us that we have found where space ends. It may be telling us that space, smooth, continuous, geometric space, is itself an emergent concept, a macroscopic approximation that works beautifully at large scales, but simply does not exist in any fundamental sense below a certain scale. Think about temperature. Temperature is something we experience as real and fundamental. You know what it feels like to be cold, to run a fever, to step outside in January. Temperature has precise mathematical descriptions, laws, and entire thermodynamics built around it. And yet temperature does not exist at the fundamental level. There is no temperature in an individual atom. Temperature is what happens when you have enormous numbers of atoms, each moving at speeds drawn from a statistical distribution, and temperature is a word for the average kinetic energy of that distribution. Zoom in to a single atom and temperature stops being a meaningful concept. It was never a property of atoms, it was a property of atoms in large numbers. What if space and time are the same? What if the smooth, continuous, and geometric spacetime of general relativity is an emergent property of some more fundamental structure, the way temperature emerges from atomic motion? And below the Planck scale, you are not in a smaller version of space, but in the more fundamental substrate from which space is built. What if the Planck scale is not where space ends, but where the illusion of continuous space is replaced by the reality of what was always underneath? This idea that space-time is emergent is increasingly popular among theoretical physicists. Erik Verlinde, a string theorist at the University of Amsterdam, has proposed that gravity itself is an entropic force, not a fundamental interaction, but an emergent phenomenon arising from the thermodynamics of some underlying microscopic structure. Ted Jacobson, in a 1995 paper that is now considered one of the most cited in quantum gravity, derived the Einstein field equations of general relativity from the thermodynamics of local Rindler horizons, essentially showing that the equations of spacetime could be read as the thermodynamic equation of state for some unknown quantum system. If Jacobson is right, general relativity is to quantum gravity what fluid dynamics is to molecular physics. The fluid equations are perfectly accurate at human scales, but they do not tell you that water is made of H2O molecules. The Planck scale, on this view, is not the bottom of a ladder. It is the scale at which the fluid approximation breaks down and the molecular physics asserts itself. It is the scale where the temperature concept stops working and you have to go back to counting individual atoms. Except in this case, the atoms are not atoms. They are whatever the actual fundamental constituents of space-time are, and we have no confirmed idea what those are. We have candidates, we have frameworks, we have beautiful mathematics, but the actual thing, the thing at the bottom, remains for now unknown. That is the reframe. Not space ends here, but here is where we find out what space was made of all along. There is a photograph, or rather the product of a year's worth of radio telescope data processed into an image that captures something about where we are. It is the image of the black hole at the center of the galaxy M87, produced by the Event Horizon Telescope collaboration in 2019. You have seen it. The orange-red ring of superheated gas, the dark shadow at the center. That shadow, the event horizon of a black hole 6.5 billion times the mass of the Sun, is a boundary beyond which our physics fails. Inside it, the density approaches infinity. The geometry of space-time breaks down. The classical equations cease to apply. What happens there is, in the absence of a theory of quantum gravity, unknown. The fact that 200 scientists across 17 countries and 4 continents, using 8 radio observatories simultaneously, could reconstruct an image of something 55 million light-years away is one of the most extraordinary achievements in the history of science. It was a genuine triumph, and yet that image captures only the boundary of our ignorance. The physics that breaks down at the event horizon is the same physics that breaks down at the Planck scale. The singularity at the center of M87's black hole is, in current theory, a Planck scale object, a region where the quantum structure of space-time dominates. Understanding what is actually inside a black hole requires a theory of quantum gravity. We do not have one. The image shows us where the unknown begins. It does not show us what is there. Compare this to the Apollo program. In the 1960s, the technology required to land a human being on the moon was at the absolute edge of what American engineering could produce. The Saturn V rocket, the Command Module, the Lunar Module, each was an achievement whose margin of safety was terrifyingly thin, whose engineering problems were solved not years in advance, but sometimes hours before launch. The program at its peak consumed 4% of the entire United States federal budget, employed 400,000 people, and required a decade of concentrated national effort. It was, by any measure, an almost impossibly ambitious undertaking, and it worked. What would the equivalent undertaking look like for quantum gravity? Nobody knows exactly, because we do not yet know what success looks like. The detection of a Planck Scale signal, whether in the cosmic microwave background, in the spectrum of Hawking radiation from a primordial black hole, in the subtle energy dependence of gamma-ray photons from distant astrophysical events, might confirm or rule out specific models of quantum gravity, even if direct observation remains impossible. New mathematical tools might unlock the non-perturbative physics of string theory or close the gap in loop quantum gravity between the quantum theory and its classical limit. These are not fantasies. They are live research directions pursued with genuine seriousness by some of the most talented physicists alive. What we can say with confidence is this: the Planck scale is not a footnote. It is the center of the deepest questions in physics. Why does the universe have the laws it has? Why are the fundamental constants of nature the values they are? What happened at the very beginning of time? What is inside a black hole? What is space? What is time? Every one of these questions leads by a short road to the Planck scale. Everyone requires a theory of quantum gravity to answer. Everyone remains, as of today, genuinely open. Max Planck, in that Berlin lecture hall in December 1900, could not have imagined any of this. He was a conservative man who had found a mathematical trick that fit some data and was not at all sure the trick was real. He gave his lecture, sat down, and the universe went quietly about its business of containing, at its deepest level, a structure that would take humanity at least another century even to begin approaching. The irony is perfect and does not require embellishment. The man who gave his name to the scale where all of physics becomes uncertain was himself, at the moment of discovery, completely uncertain about what he had found. We are all still sitting in that lecture hall. The questions are better. The tools are better. The distance to the answer is, we think, shorter than it was. But the answer has not yet arrived, and that, somehow, impossibly, is the most exciting thing about it. Not that we know, that we are still going. The universe kept its deepest secret at the smallest possible address, and we have only just found the street.